Do I look all right, you guys? All right, here we go. Good afternoon and welcome to this week's CERIAS Security Seminar from Purdue University. Our speaker this week is Dr. Chris Jenkins, who is a member of the senior technical staff from Sandia National Labs. Chris?
Thank you for the introduction, Drew. Once again, my name is Chris Jenkins. I work at Sandia National Laboratories in Albuquerque, New Mexico. And we're going to speak to you today about a new research topic, looking at new ways to protect computing systems. And for us, we came up with a concept called integrity levels. So as a summary, this can give you a vision. So imagine you have a computing system and detects a loss of integrity. And so it's going to migrate to a different level of functionality or behavior while taking steps to reestablish higher or different levels of functionality. So the way we wanted to make an analogy to biology, if you have, say, an H1N1 on the swine, you typically have a different antiviral drug for each strain of the flu. And so we thought about what if your body could naturally mutate to thwart the virus. So how would you do that in computing? So if I put malware in your computer, instead of having an antivirus signature, instead of having ways to detect Trojans, what if your computer is naturally mutated such that the virus or the Trojan no longer could affect it? The environment could change dynamically on the fly. And so that concept is what we call integrity levels, and today I'm going to present to you the way that we design it. So the goal of this work, as I said earlier, is to design a polymorphic computing environment. In particular, we want to operate with compromise present. So a lot of solutions focus on detection and prevention. Can I detect the virus? Can I detect the malware? Whereas we're going to assume that attackers can't get into your system and you will have some compromise on it. So how would you design computers differently with this assumption and have the ability to degrade predictably? Also reduce the amount of trusted computing base to potentially allow formal verification. And the big one is we want to run legacy design systems. So computing has been done over the last 30 years. We don't want to throw all of it away, so there has to be a point to the work. But a lot of the newer platforms that we have today do have hardware-based security features, and we want to use those as well. So the overall goal of this work at the lab is to prove this idea with a proof of concept implementation. And the outcome has been, one, we have a working tool chain, and we do have a proof of concept that I will show you throughout the presentation. So today, we'll speak in various parts of the work. So the first is the motivation. Now, why is this being done? Then we'll move on to what we call integrity levels and how to design those at a very high level and also dive into some of the details. We'll look at our methodology and prototype that we have come up with, as well as the future direction that we see for this work. So I've given this talk a couple times, and the first question I usually get is how did I actually get on this project, since I'm actually a new member at Sandia. I've only been there, I think now 2 years and 2 months, so kind of fresh out. So this particular project came out of what we call Early Career Laboratory Directed Research and Development, or ECRDRD for short, and it's usually for newly hired PhDs that have finished their degree within 1 to 5 years. It's competitive in the sense that you have different rounds of proposals, and you have to go to what's called an investment area review. And if you are selected, in this case my project was selected, you get a budget for 2 years to pursue this idea. And in this case, it's to actually pursue a proof of concept implementation. And so the goals, as you probably can guess, I have to report every quarter to an investment team to make sure that I'm actually using the money wisely. You have to present, as I'm doing today. When I get back to work on Monday, I will get back to writing some publications. And then, of course, looking for collaboration to potentially move the technology readiness level from a 3 that we believe we have now to maybe a 4, 5, or a 6. So now let's go back to why is this work being done? So if you read the news today, you can probably agree that existing protections are not enough. And so we're looking at how do you build a system where instead of actually adding on different components, it's actually by design to be resistant to malware. And probably the most important aspect of this work is can we apply it to traditional computing as well as outside traditional computing, or wide applicability. So let's look at the current landscape. So we have different types of attacks. And just to kind of go briefly over the attacks listed, can I see your data? Can I modify your data without you knowing in terms of integrity? And can I prevent you from accessing your data? Now, there's different attack vectors in terms of how to make that happen. So one, software, as the name implies, you just use software. Can I look at your network? Can I actually maybe remove the device and do some probing on it, as well as the infamous and sometimes fun side channel attacks? And so typically most solutions that we see, they tend to focus on either prevention, we don't want it to happen at all, can I detect it, and typically if I can detect it, I want to recover, and if one of those three options are not possible, then you want to have some evidence that you can actually, that you have been attacked. So the challenge with the work is coming up with the model, which typically people say is you can come up with a lot of different models, but can you actually build it? Can you actually move it to implementation, which typically is the challenge. And we'll get into some of those challenges as well. One, no one wants to throw away 30 years of computing, so typically can you support existing systems as we build them today, as we have them today? And then the cost of what I'm saying is the 3 C's: computation, complexity, and confidence. How's it going to affect the performance of it? If it takes 2 developers to make a system and I add integrity levels, is it going to take 20 developers? So how much does it change the complexity? And of course, confidence. Is it going to work in the manner that we think should work when it should actually happen? And of course, the last one, can we have tech transfer? 7 years from now, you go down to Best Buy and buy a computer that has integrity levels installed in it. If you've seen a lot of, in the news, a lot of vehicles are going to be communicating with each other. So can your vehicle have integrity levels in it? And so that's really, can the market actually support this type of technology? So some of the major threats, these are not the only 2, but these are probably the big ones that get a lot of notoriety in the news, are 0 days and advanced persistent threats, also known as APTs. So 0 day, as the name kind of implies, there's no patch available. It's been 0 days since a patch has been issued. Sometimes that's not always the case. Sometimes a patch has been discovered, it just may not have been released by the company or the software vendor. And so the way we typically defend against them is just have defense in depth. So if you need to go through 20 doors to get to what you're trying to attack, and 5 of them have 0 days, I still have 15 doors for you to get through. So defense in depth. Advanced persistent threats typically tend to be a little bit different. Whereas 0 days are done really widespread across many different machines, APTs are really about persistence, and they tend to be targeted. So I want to get into a particular machine, maybe a particular location for a particular reason. So they tend to have more substantial resources, funded much better. And they, I would say, use multiple vulnerabilities as a bigger attack surface. And so their goal is to get in, get the privilege that they want, stay there, and then potentially propagate to other computing systems if they choose to do so. So now we want to look at a quick game of cat and mouse. So if you're familiar with the different ways that attacks have been done in the past, in some sense today as well, you have these type of attack vectors, or I should say, correct, attack vectors. And so some people came up and said, well, if we put data execution protection, or DEP, also called the index on some other architectures, it makes it harder to actually do these type of attacks. So what is a typical attacker going to do? We're going to come up with another attack. In this case, we turn to libc. So we came up with something else called address space layout randomization. So attackers said, wow, that kind of hurt me, so I'm going to figure out something else to do. We're going to come up with ROP, or return-oriented programming. And of course, there are some, in this case, K-Bouncer and ROP Defender, some research, and there's other papers as well. So the other question to ask, is there something else? So if you think about all the different ways, and this is definitely not an exhaustive list, that we are using to protect our computers today, the question has to be asked, is the paradigm wrong? Is there something else that we can do to make your system inherently more difficult to attack versus just kind of adding on patches? And also, by the way, if you have any questions during the talk, feel free to ask as well. So now we're going to go through some hypothetical use cases. These cases hopefully will give you a high-level view of if a system had integrity levels, how would it function? So once again, having a wide applicability, we're going to look at 3 different examples. So look at traditional computers, look at smart meters, and also if your car wants to start talking to other cars, how it potentially could behave as well. And so the thing about these different I'll say use cases is that they're very different application spaces. So think about what has to be the same between them and what has to be different. So the first use case is we're at integrity level. How do we actually navigate down? So in this case, we have an app, your typical rich operating system. So it could be a Windows, Linux, Android, iOS. A real-time operating system for your baseband processor, and then for our particular example, a security app with a hypervisor running on the hardware. So the scenario that we're going to look at is your operating system is going to remap the vector or system call table. So your hypervisor is going to say, you know what, this is not really something that typically happens outside of boot time. So it's going to notify a security app that, you know what, this happened. I don't know if it's good or bad, but you wanted me to listen for it, so it has happened. The app is going to confirm that, you know what, yeah, this isn't normal according to the policy installed for that system. So the security app is going to say this computer system is now at some level lower. So what does that actually mean? The new level may be that you can't write anymore at that particular table. It may be that you restore the table, or it may be anything else that your imagination can find it. But that is just a hypothetical example of how you can write to the table, so the malware can get into your system, and it can actually overwrite your system call table, also known as a rootkit. But once you downgrade to a different level, or integrity level in this case, that can no longer happen. So how will malware react? We don't know. But that shows you the case of navigating down. Now the question is, if you can navigate down, how would you navigate back up? So our example is that the user wants to execute an API to process sensitive data. So once again, the hypervisor is going to notify security app and say, hey, I received this call to say some sensitive processing wants to be done. So I'm going to disable all network interfaces. Security app, in this case, is going to increase the integrity level because you know for a fact that network communication is blocked. So you have more trust that if something goes wrong in your system, it's not going to get out. But you could potentially still have a way to get out, but maybe it uses a security app or some very proxy way or filter way of getting out of the system. Another option that we thought about is maybe we just tag network packets. So as you have a router or a switch, your computer coming out, is a 5, your computer coming out to me is a 7. And so how do you handle those connections? Maybe the one that's a 7 goes to a different proxy server than the one that's a 5. Once again, it's a hypothetical, but it kind of shows you the concept of that your computer is viewed differently based on compromise or not compromised. So those are more traditional computing. So now we're going to look at something that you probably don't see every day, but smart meters. So how would integrity levels apply to smart meters? So we're going to assume that someone that has a smart meter at their house, wants to tell the power company that they're using less power than they really want to. So they get a network packet that is sent to the device, potentially over Zigbee network, and it's going to say run some commands that either aren't typical or out of bounds, out of range. And so the determination is that it is out of bounds, and so the navigation would be we're going to prevent the execution based on the policy that's installed in that system. We're going to downgrade the integrity level, and in this case, we're going to move away from a smart meter and go back to a dumb meter. Reason being that the power company or water company still wants to know what you're using, but that smart functionality, let me say it again, the system figures out that smart functionality is probably being attacked, and so we'll just move down to a different level so that you can't attack it anymore. So the functionality of the device is changing based on either compromise or, in this case, potential compromise. So the last one, automotive systems. So you have different components. You buy a car that's 10 years old or 12 years old and it has 10,000 miles on it, you might want to be careful. So you might want to protect the odometer. You have safety systems. So some cars now are getting more and more digital such that your brakes, gas, and other components are all digital as opposed to maybe hydraulic or other more mechanical-based systems. And then, of course, you have infotainment. So for our particular work, we believe that it's more practical for the infotainment section of your car. There's nothing about the real-time partition. Real-time meaning if you put your foot on the brake, your car has to stop. You put it on the accelerator, it has to go. So there's nothing about our design that we feel like those systems can't use integrity level. We feel like they're more practical for infotainment systems. And I can't remember the actual paper, but I want to say it's from a university. And I remember that they took a CD, they put the CD in the CD player, and they locked up the brakes. So, and the way they were able to do this is because all your devices in your car were on something called a CAN bus. Are people familiar with the CAN bus? So if your braking system is just listening for a packet, and it gets the packet to say, apply brakes at, 0.5 of the power, that's exactly what it's going to do. So we, of course, wouldn't suggest shutting off the car as a downgrade option, but maybe there's some ability to either disable certain devices or some organized shutdown. And so this kind of a quick picture. Here's the CAN bus. Everything's connected. And so if it gets that signal, it's going to go ahead and do whatever that packet tells the system to do. Now, for most of this work, we're looking at how to stop attackers from getting into the system. Kind of a side work may be that we can increase reliability of certain application spaces or different domain spaces. So before I get into some of the details, are there any questions that we have? Okay. So I've said this word integrity level a couple of times, but really what do I mean? And so we decided that integrity levels have three different components: a model, an architecture, and a policy. So the model just describes how does the system really work? How does the data flow? How does the control flow work? Architecture, as we said earlier, you can build a model, but can you actually build it? So architecture says what has to be present on a given system such that this concept can be built. And the last is policy, which is how your system changes based on environment stimuli. So those three components, we believe we can turn a computing system into a system that has integrity levels. So the approach that we looked at and this is kind of getting more back into traditional computing, we looked at the OS app model and said, what about that do we think we can change? And so we decided to move from that model to what we call a four-domain model, as you see here, and we will get into each of those domains throughout the talk as well. We focused on being able to prototype this idea rapidly with open source software. We generated a grammar, so I tell you that we can write a policy, but how do you actually write it? So we developed a grammar to actually write policies and test them out. And then also mindful of the three C's as we build the system. So kind of similar to our goals. So we come up with more or less a framework and not a solution. I would argue that there are a lot of different solutions that target different segments that we're trying to work on as well. And so instead of competing with them, because as a lab, we don't compete with industry, and we're also not a profit, we wanted to make a framework so you as a system designer could choose the solution that you want to put into your system. And some solutions are network-based, host-based, analytics, big data, cloud. In this case, we're focused on being host-based or close to the compromise. We can run legacy design systems, and we're looking at, in particular, altering the behavior or functionality of a system when it does have compromise. For our prototype, we don't use any of hardware-based security features, but we could use them. And so now, some of the challenges of this. The first one makes sense, right? It's a new model. You can't go buy this. You can't actually see how it's going to work in terms of a large-scale deployment. For our particular prototype, since it's a really basic prototype, we don't have a lot of fidelity, but we believe that is based on our prototype. Given more time, given more people, we believe that can change. And we believe it's feasible to build because we do have a working prototype. Some other potential features of this work is, one, you can't have remote attestation, which is to say that the device is in a state that you do trust. Probably one of the unique features of the work is that we have declarative policy that is separate from the implementation, meaning that I can give you two different computing systems. Both can say that they implement integrity level 3.0, but they have their own unique implementation. We don't generate any policy on control flow graphs, but we don't see why you can't do it. So that could be another benefit of this work. And probably one of the unique points of it, if you go back to the slide about the game of cat and mouse, you see that most of the way that we patch something up, we fix something, was really fixing a particular attack vector. And so the attacker just moves from one attack vector to another one. And so what we're looking at is, well, let's stop trying to fix attack vectors, and let's actually try to look at what we call event points, which is what is the actual point that has to happen, or the actual event, I should say, that has to happen in the computing system for the attack to be possible. So one way to think about this, if you think about malware, what actually makes malware malware? And I'll open that up to anybody that wants to take a shot at that. Don't be shy. But in a sense, malware has to get, one, it has to get CPU time. It has to actually execute instructions on the computer. And the second one is that it has to actually get code into your computer. So it doesn't really matter about how that happens. The event point is that it has to happen. So why not look at how to protect that as opposed to your attack vector? So we'll dive now a little bit more into the details. So the threat model that we have is that one is a trusted supply chain. So if I buy a computer part and it says it does X, it does X. And then the second one is that we have a trusted authority that we can communicate with. So somewhere in the world, a system with integrity level can actually communicate with that trusted authority. For our prototype, we effectively use none of these, but that's just the threat model that we started out with when this idea first came to fruition. As far as the domain, the key thing to remember is that they're all independent. They're going to have a certain data flow model. We'll get to that in some of the other slides. And that there's no pass-through ability. So if something goes on in the reporting domain handles that, and then it passes off the information as necessary. And then as you can kind of get a sense throughout the talk, it's really big on availability. How do we stay operational with compromise? Because our assumption is that we will be compromised. So now let's move into the different domains. So the function domain, as you probably can guess, is actually typically what we call the function of the computer. And for traditional computing, typically this would be a virtual machine. But it's effectively where your computer does all the computation as you see it. The reporting domain reports to the policy domain, hence the name reporting. And for our particular case, it looks at what we call complex events. And when we get into the prototype, we'll speak a little bit more about complex events. And it also maintains a little bit of historical data based on logging different information within the system. So now the enforcement domain, once again, as the name kind of says, is it actually going to monitor the function domain is going to enforce the policy. So if a policy says you can't overwrite a system call table, if it says that a packet from the network can only run this particular code, it is going to make sure that happens. And if it doesn't, or something goes out of bounds, it's going to notify the policy domain that, hey, this occurred. And of course, the policy domain, as once again the name implies, contains the policy, it can update it. It is the only one that notifies, or excuse me, is the only domain that's actually aware of something called integrity level. The other three have no idea. Right? If your enforcement domain says that this particular range of memory or this peripheral is no longer there, then it's no longer there. But only the policy domain actually is the one that says go ahead and do that functionality. So a quick example might be you download a PDF from the web. I guess I gave you a better example. Let's say you take your web browser. Now, if you click File Open, you typically can see all the files on your computer. So what if now I change this so that when you click File Open, you only saw the cookies that your browser has to use for your different websites? So in one case, you see the whole hard drive. In one case, you just see the cookies. So, and your policy would dictate when you saw one versus the other. And so whenever something happens, either in the FDED or RD, of course, the policy domain or PD gets notified. So that's the model, and that's how the four components work together. But as I said earlier, how do you go from model to implementation? How do you actually build such a system? So for this particular work, we're going to focus on von Neumann or Harvard architectures. But if you went to smart meters, electronic voting, medical systems, every single application domain would have its own unique architecture. So we're going to focus on kind of traditional computing for this talk. So we said that the enforcement domain must be more pillars than a function domain. The ED and RD may exist at the same level. We see no difference if they're at different levels. And the policy domain should have a higher privilege or separation. So things to know is that there's a must, there's a may, and then there's a should. And we'll get to why that's important in the next slide. And then the function domain and policy domain never taught. And so we read a paper out of, I believe, CMU, the university came out of, and they had a good paper on how to make a hypervisor, or in this case, integrity protected hypervisor. And they came up with these 12 rules, and looked at Zen, KVM, I think maybe VirtualBox, VMware. And we saw really no reason not to include them. Their paper was pretty outstanding, and it shows that if you have these rules, your hypervisor will not be attacked. So we have the ones that we specify plus those 12s as the requirements to build such an integrity level system. So now we're going to go through some potential ways to build it, and then we'll show you the way that we built it for our particular prototype. So in this case, hardware has the higher privilege, hypervisor has, I guess I should say, the most privilege, and then you have the FD, RD, and PD in terms of virtual machines. So they have the least privilege. And so earlier I said you have I think a may, a should, and a must. So your ED must have a higher privilege than your FD. Now, we said that probably since your policy domain is what you want to protect most, you may also want to move it down. It becomes, again, the choice of the designer. So we feel like a better option, kind of going with the principle of least privilege methodology, that you actually put an enforcement domain in the VM as well, and just put the specific parts that have to be privileged. And here we call it stub, but really just the parts that have to be privileged into the hypervisor. Another architecture, this is kind of more of your traditional architecture where your function domains at the lowest level and the other three are at the highest level, or I should say a higher level. And this is the way we decided to build our prototype. So what if you wanted to really put this into an actual real system? So we thought about putting this onto ARM trust zone. Now, are people familiar with ARM trust zone by any chance? I see a couple of heads nodding no. So ARM, I believe in 2003, came out with an SOC methodology of how to separate your computing into what they call the non-secure domain and secure domain, not to be confused with the four domains that I just described. And so they actually have 3 privilege levels inside of the actual non-secure domain and 2 inside of the secure domain. And so if we want to take the integrity levels and map them into this architecture, our potential mapping will be as follows. Your function domain will effectively be a virtual machine using the bottom 2 privilege levels. We'll put your ED and RD in terms of your privilege level number 2, and then just because you want to protect the policy domain, since it actually has all the information, we put that in security domain, in this case at PL0. So this is how we would do it on ARM. But what if you wanted to put it on Intel? So Intel has a little bit more complexity, I would say, in terms of its architecture, but it can also be done as well. So if you were in VirtualBox or you were in VM, this is effectively the equivalent way that it does it today. Then we would just put the other domains as you see here with the policy domain at the higher privilege level. And so the last way that we thought maybe we can build it is what's called Intel XGX, or software guard extensions. So these extensions are not yet available in any processor you can buy. So I believe whatever the next processor coming out will be the first processor that has these extensions. And so we're not really sure if SGX uses rings or not. I just read a lot of different white papers on this. But since it's a newer technology, we said, well, how will we build an integrity level system with this technology? And so for us, and I guess just go a little bit into the technology, they have this concept called an enclave. So you have your OS, you have your particular application, the stack and code, and your enclave is encrypted by the memory at memory speed or at line speed. And so we felt, well, since that's encrypted, we could put the PD inside of there and put the other domains in the same places as the previous slide, or put everything inside the enclave, but leave the functional domain outside of it. So you would still, so if something happened in the functional domain, the enforcement domain would still notify the actual policy domain what happened, but they would just be encrypted and then decrypted on the fly as they go from effectively the memory to the processor. But once again, this isn't out, so we don't know how the performance cost would be. So once again, going back to the 3 C's. So spoke about model, spoke about the architecture, so we'll touch a little bit on the policy. So a book I recommend called Computer Security by Matt Bishop kind of breaks down security into this, I should say policy into these states. So security policy is about authorized and unauthorized states. So a security system is that, hey, I want to start in an authorized state, and I never want to leave that. I always want to move to another authorized state. And of course, you have a breach when you move into an unauthorized state. So that's the way that the book presents security policy. So we're looking to slightly change those definitions. So instead of authorized and unauthorized, we're looking at either more secure and less secure states, or you can think of it as more functional, and less functional states. It still applies. A level for us is the set of authorized and unauthorized states based on environment stimuli. And what's really different about this work is that a breach occurs when you move into an unauthorized state, but your authorized and unauthorized states can change based on your level. So what may be authorized at one level may be unauthorized at a different level. So that's kind of how this work compares to kind of the standard way that we think about computer security policy. So how do you write policy? I mentioned earlier that we have a way, or excuse me, we have a grammar of how we want to write our policy. In our particular case, we have a language called XACML, or Extensible Access Control Markup Language. Is anyone in here familiar with XACML by any chance? Have you used it for a project? No. Okay. So it's kind of a somewhat newer model, I think I guess within maybe 10 years, which can maybe, I guess, historic in computing terms, but you have mandatory access control, discretionary access control, role-based access control, and XACML is attribute-based access control. So just kind of a newer way people are doing access control. So the current guide is at 3.0. As you can see, 2.0 was ratified in 2005. And Bank of America, according to a website, Axiomatic is the actual website, but Bank of America, PayPal, and Boeing actually use XACML somewhere within their infrastructure. And so why did we decide to use it? So effectively, there's a language called Alpha that makes my life really easy in terms of prototyping, or axiomatic language for authorization. And it has a really nice Eclipse plugin that converts Alpha, which I'll show you some examples of Alpha and XACML in the presentation, but it converts Alpha to XACML 3.0. So it makes my life a lot easier, and it's real simple how to write the actual grammar. And then, of course, because it is a standard, you can always compare it to other implementations to see if it works as intended. So now we went over the model, the architecture, and the policy. So now let's look at the prototype. So before we dive into it, what are some of the questions that we had before we started to build it? So the first one about the model is it the right model? Does it make sense? Do we need more domains? Do we need less domains? What data should be passed between the different domains? From the architecture, and probably throughout the rest of the talk, I'll speak about a runtime engine. But is it efficient? We're taking effectively an XML document, doing some transformations on it, and then putting it into a runtime engine. So is that the most efficient way to do? Does it work? What are some of the trade-offs? Can I put some things in hardware that maybe I want in software, or vice versa? And are there any other requirements that may be outside of what I described earlier? And then for policy, how do you generate an actual grammar? What is the best choice? Alpha is just one language. There's other languages as well that we can use. So these are some of the questions we're looking for the prototype to hopefully flesh out in terms of improving the technology readiness level of this idea. So our methodology, phase one is really what I just described to you. It's the core idea. Just coming up with all the pieces. Phase two is we decided that based on time and effective time and money that we wouldn't be able to build the complete prototype as we envisioned, which was, I believe, on an ARM trust zone. So we use a slightly smaller model. And in phase three, which is where the work is currently at, I had 2 interns working for me this past summer in phase three, which is we wrote a test harness effectively writing a new system call inside of the Linux kernel. And then phase four, which we may or may not get to, is actually putting this on either a Raspberry Pi or a trust zone platform and then attaching it to the internet and putting a web server on it and see how it performs. So I mentioned earlier that we have the concept of attack vector. Why look at that, but look at the event point? So when we started doing some of the developing for the prototype, we found that it was hard to actually model platform-specific events that are ubiquitous. So there are registers on ARM, which are different than Intel's, which are probably different than Freescale, which are going to be different than medical devices. And so there was no universal way to do it, but you do have platform events that are very, as the name implies, platform specific. So we decided to have a semantic event which can be universal across all policies. Still may be different semantic event for a given application space, but I can say don't write to this particular address space. And really, if it's ARM, Intel, Windows, Linux, Mac, that concept is the same across all of them. So it makes it a little bit more portable. And then there were also some events we wanted to monitor, but they didn't really fit into platform semantics. So of course, you give them the name complex event. And so these are events that really require both time and space and can't really be described with either platform or semantic. And so the reporting domain would really, by capturing historical data, could actually capture these events. So a quick example would be if we took a process and we said that it's in the runtime queue, but it's not in the process queue, or I say the task list. Does anybody know what that is? So the process is running, but you can't see it in the task list. It's a hidden process. And so really, it's hard to represent that as a platform or a semantic event. And so if you monitor in the right points in memory, you can actually see that happening. And so we can consider it a complex event. And not just processes, it could be anything, installing Linux kernel modules, so on and so forth, but something that has a little bit more complexity. So our concept is just that, a proof of concept, very basic. This is our particular design, and I'll give you a couple of screenshots later on to actually see the development environment I'm working with. But we frankly have BusyBox. Are people familiar with BusyBox by any chance? So some are, some are. So BusyBox, you can think of it as a very, very basic user interface. We run that over Linux, and then we run both of those, I should say, over a hypervisor that is called Xvisor, which is an open source hypervisor for both ARM, x86, and MIPS, even though I believe MIPS now they're no longer supporting. And we go from alpha in our tool chain all the way down to a .h file, header file for our C programmers. So we're working on an upgrade demo right now, but I will be going through the steps of how we did a downgrade. So first question should be, I have this nice model. I tell you how to build it. So now the question is, how much size do I add to all the code? I have an existing system. I come to you, you come to me, and you say, you have this new idea. I want you to put it in. What's it going to do to my code size? So we took our concept, we put it in. We have a final image, in this case, of 5 megabytes. All of our code, based on the previous example, are specifically inside of Xvisor. So we're going to look at the 960 kilobytes or slightly under a meg. And so what we see, if we look at all the different domains, the shim is part of the code that's specific to the platform, whereas everything else is more platform agnostic. And then the commands part of the code are really just for me to be able to look into the actual what's going on, what's running, what's not working, more so debugging. So if we remove the commands part that you probably wouldn't have in an actual finalized production model, we see that the amount of code needed for the test I'm going to show you next was only 1.6% of Xvisor, and of the final image, I mean, you're getting to 0.0 something. So it shows that for not modifying a lot of code, you can actually still get a lot of functionality in terms of what we want. And so if you remember, some of the goals of the project was, one of the number one goals were reduce the trusted computing base. And so in this case, I'm taking a 5 megabyte image. Typically, you would have to trust the entire, I would say, either Xvisor or trust Xvisor and Linux and probably the firmware. I'm saying now we're just going to add 1.6% more code, and really that 1.6% is your trusted computing base. Realistically, it is the entire Xvisor, but it shows that we don't have to modify a lot of code to add integrity levels. So now we're going to back up just slightly, and how would you actually implement an integrity level? How does it actually work? And then I'll show you the demo at the end. So first, you write the rule. For the demo I'm going to show you, our rule was you cannot overwrite the system call table, which is a common thing that most rootkits and nasty malware does in your system. Because once you hook the system call table, you pretty much can do a lot of different things within your system. So we write that rule in alpha. As I said earlier, Eclipse takes that rule set, converts it to XACML. Then a parser that was actually written by one of my interns for that summer actually converts it to a C header file. And then when we actually start the system, a few more things are done to actually have a run integrity level system. In this case, we attach the system map, in this case of Linux, and we initialize a few hooks to make sure that we can actually monitor the different aspects of memory that we want. And once again, this is all done based on the policy that's been written in alpha. So this is actually alpha, and this is actually says don't overwrite the system call table. So the grammar for alpha is something we came up with. It's still an area of open research. So you could specify this concept in a different way. This is what we've just chosen for a particular prototype. So our event is to write. In this case, we just have a string system call table, but the runtime engine actually converts that to a location in memory based on the system map during initialization. And so that's really the beginning vector, I'll call it, and then 1,456 bytes after it is the actual we're going to mark as our region to protect. Deny it, and if you do see it, change the integrity level, in this case by -1. Could be -2, -10, whatever you want it to be. It could be some other mnemonic. We're just using numbers just to keep it simple. So alpha gets converted into a XACML, and as you probably can tell, XML is a lot more verbose. So I was really enjoying using alpha as opposed to having to write all of the XML. But it has effectively the same concepts. Deny the write. It's event. The function is called in address space. I'm looking at system call table, the size. And what happens when you see it, we need to deny it and go down -1. So all the information is still there, but as you can see, it's a lot more verbose. And of course, you can have a string presented to the user or send an email, whatever else you want to do as well. And so just a little bit more with the parsing for the XACML. You have a top level which has all your policies. We have something called, we actually just call it integrity level .h, and that really is the grammar. And so we can take the policies in XACML, we can take our grammar, combine the two, put them through a parser, and actually get a header file that can be parsed by the runtime engine to do everything else within the system. So as a quick look at the C header file, this is not the complete header file, but this kind of shows you for that particular rule that all your components are still there. It's a valid rule, write to it, where to write, the size, the function, and what to do when you see it happen. So now I'm going to describe just a little bit about the test harness and then give you a quick screenshot to show you how this actually works, or to show you that it does work. So we added a new system call to the Linux kernel that effectively is going to mimic a rootkit overtaking your system call table. And so we can go to BusyBox, which is our interface. We can say, overwrite system call 45. And when that happens, our system effectively should catch it and let us know that it's been trying to do this, and then either block it, let it go, or whatever remedy you want to take based on the policy that we have designed in alpha and put into the runtime engine. So I just want to go real quick over actually the steps of how it truly happens at the architecture level. And so effectively, you do the command to write the system call. A data abort will trigger, regardless of if it's ARM, Intel, or any of the other kind of virtual machine-based processors. Virtual memory-based processors. So the data abort is going to jump to effectively a routine call, also known as the interrupt vector table, which is, of course, again, the same across the different processors. Organization may be different, but the concept is the same. It's going to generate an appropriate event. In this case, it's going to generate a platform event, take that platform event, and convert it into a semantic event that can then be analyzed against the policy that's been put into the runtime engine. Determine the reason, go through a few objects. If nothing has been violated, you just go back to a sunny day. But if something has been violated, you can either notify the policy domain or any other further callbacks if necessary, and then you pretty much return. And just to give you an example, this is done probably, 100,000 times a day on your computer. But it's done so quickly that you hit a keystroke, you don't think much about it. You just see the letter K or A appear. But a lot of this has to happen. You hit the keystroke A, a lot of this has to also happen as well. So we're kind of following that same methodology. So a little bit diving down to the call. So we said we use BusyBox. So we add a new system call, and this calls the system call on our behalf, and it passes the appropriate parameters. So overwrite system call table at this location with this value, so on and so forth. So inside of the kernel, There is a system call table effectively the system call table effectively will call this particular function at some point in time because it's the new system call that we added. It looks at the parameter, figures out what functions we want to use. In this case, write system call entry, and so this will mimic overriding the system call table. So this should trigger, if designed right, something with our integrity levels to say, hey, we took a policy, we put it in a runtime engine, we have a test bed that allows us to write to a location in memory that should not be allowed to happen, so does our solution work or not? So in the next slide, I'm going to show you a screenshot. Unfortunately, I do not have a live video, but I can describe it very well. So we're going to have one window that's going to show you the busy block shell, and then, of course, another window which will be going into the hypervisor, in our case, xvisor. So xvisor is up top, busy box is down below. So in our case, the busy box is the FD or function domain, and xvisor contains the enforcement domain, policy, and reporting domain. So we're going to look at the top window first. We're going to look at xvisor. So we have, in this case, we have setup, status, see some twos, we see a one, and then we move it. And so at the bottom of busy box, we're just issuing effectively the same system call over and over again. And at some point, this bad function comes out. So what happens? So we set it up, we check the status. So our system is telling us that according to its status, that it is at an integrity level of 2. Whatever that might mean may be different for different application spaces, but for our prototype, we just set the number to 2. So we issue the system call, and it's going to drop that number down to 1. At the new integrity level, and now this doesn't let it work at all. And so you can issue another system call, nothing's going to happen. It's going to say, yeah, I know what you're trying to do, I'm not going to let you do it because the policy says not to let you do it. So then once we actually remove the integrity level, the system keeps running. We issue the same system call test bed again, and it actually overwrites the code. So you do it again, you've actually changed that system call to point to what we said was another function that is printing out the word bad function. And so now, effectively, your system has been attacked or has been hosed upon, or whatever word you want to use. So this shows you that given a policy written in alpha and put into a runtime engine and set up the architecture in the correct manner, you can actually have functionality, in this case, the ability to write a particular memory location, work or not work based on your integrity level. So what did we learn from building this prototype? Same question that I have today, that I probably have for a couple more months, is what is the appropriate taxonomy? You know, and is alpha or is XML the best choice? Because the question that we're always going to have is, can we actually express all the states we want? So the holy grail would be, can I take my grammar, write a policy such that all malware that comes into my system inherently will violate this policy based on what it wants to do? And if I can do that, effectively, I've written a specification for my computer. And so when malware tries to look at the wrong files, a violation will occur, and based on the policy, you will have some mitigation. Also, fidelity. We used a lot of, for lack of a better term, virtual machine introspection. But if Linux can also interact, or I should say if the FD can also interact with the ED, does that change how you write policy? For our prototype, we don't have that, but it could potentially change what you want to do. There are also policy and rule combining algorithms in XACML that we didn't look at, but it does have. And so we don't know if those present a security issue if they're combined in the wrong manner. Could you potentially skip a rule if you combine them in a certain way? We don't know. And then some other points, pretty much this really is about protecting the functional domain effectively. But can I have the other components also have their own levels? And we're trying to mutate a system to avoid being attacked by malware. What happens if the malware mutates? You know, how would malware mutate itself to affect the system that's designed this way? We don't know. And then, of course, the last question, if attacker can't get into the FD, what they're going to do, they're going to try to attack the other 3 domains. So what can you do to protect those? So moving to the future work, we're thinking about maybe open source the idea. We're still undecided right now. But the big things are, you know, if I want someone else to help me with this, what is the API? What is the components that you can work on to actually make this work? far as the taxonomy, also it's a grammar, we don't know what the appropriate one is. So we actually want to get more refined in that so that I can actually say, maybe describe more complex events within your system. And our tool chain right now, it works fairly well, but it's always good to have something that you can put on GitHub, you can download and it works right away. So we design it in a very agnostic sense. So outside of the shim layer, anything else is agnostic to both the architecture and the particular hypervisor. So if you wrote a shim for Zen, you can put it on Zen. If you wrote one for KVM, you can put it on KVM. And we also want to get more diverse architecture. So everything I'm doing right now is traditional computing. I would like to get my hands on maybe a smart meter and think about how would that work, or a medical device, vehicle to vehicle communication. And then right now, as one of the main goals of the ECLDRD program is to foster collaboration. In this case, I want to collaborate with other universities to push the maturity of the particular project to a higher TRL level. So, but thank you for your time.
If I just stopped recording, perfect.
I've done it a couple times.
Any questions for Chris?
Yes.
This might be in the vein of examining your taxonomy, but how do you come up with the semantic events? Like, are you looking at a known taxonomy of malware that you're looking for specific events that they have in common, or maybe that's also a secret part of what you're doing as well?
So it's not a secret part.
Okay.
That's not a problem. So what we did, I think I read about 10 papers on virtual machine introspection, and pretty much all of them focused on system call, I think the vector table, and hidden processes. Those are just common things that malware does, or to say, I consider all malware, but in particular rootkits do. And so we figure we want to publish this, take what people are looking at and saying, hey, we can accomplish the same thing, but in a slightly different manner that's not specific to any malware out there.
Right.
And so we started off with platform events, and when we realized that wasn't portable, from looking at those research papers, we just realized that, okay, these concepts are portable, and so we just started there. Over time, we would probably want that grammar to expand to include more things, but that's an open area of research.
Okay, thank you.
Mm-hmm.
I know from earlier meetings that Sandia does have a few more internship opportunities that have opened up this week. Chris is also on the hiring team for career opportunities at Sandia, and he reports to a Purdue, a CERIAS graduate from Purdue. So
that is true. That's very true.
So we are done now, but if you'd like to afterwards come up and talk to Chris about career and internship opportunities at Sandia, maybe you can help in that respect as well.
No problem. Not a problem at all.
The order is Joel. Randy Tans.
What's that?
Randy Tans.
Oh.
So quick question. Does this 00 mean that we're off air?
Yeah, we went